So let's take a closer look at the Upwind flux that we mentioned in Module 1 and see how it applies to our 1D linear solver. So if we enforce that the flow is incompressible and that we're using a 1D domain, we have to have constant flow with some velocity c everywhere. So in other words, if we're looking along the axis of our one-dimensional domain, if we have some velocity here c, if it's incompressible, then we require to have the same velocity everywhere. If it was compressible, we could potentially have velocity gradients in here, but because it's incompressible, whatever velocity we have here means that to satisfy continuity, we have to have the same velocity everywhere else in the domain. Likewise, you could have a situation where you have incompressible flow, but you have a two-dimensional domain, and then it's easy to see that you don't necessarily have to have a constant velocity everywhere. So you could, for instance, have a large input velocity here and a smaller output velocity here, and you make up for your flow coming out the sides, perhaps, as an example case. So going back to our one-dimensional domain, we'll assume that our velocity is in the positive x direction, just for simplicity. And this means that our numerical flux is then our velocity times the solution at the boundary on the left side of the boundary with respect to the direction of the x-axis. And that holds at every boundary. Now, just because it's the same overall form for every boundary doesn't mean the actual quantity is the same at every boundary, because recall that Q minus here is the upwind element. So if we consider our kth element here, then it's easy to see that our flux, if we have a velocity in the positive x direction, will be this quantity here, Q minus, but this is associated with the K minus 1 term. Likewise, you could imagine that we have a further upstream element, call it K plus 1. Well, in this case, this is still Q, this is Q minus here, and this is Q plus. Well, here our flux will also be C Q minus, but now it's this Q minus, not this Q minus. This is the Q minus associated with K, whereas this is the Q minus associated with K minus 1. So we'll see then for this element here, K, we have two fluxes across the boundaries. They're both CQ minus, but in this particular case, it's Q minus at XL, and over here we have Q minus at XR. Note that these two quantities don't have to be equal, so therefore the fluxes don't have to be equal. So we can have an accumulation or depletion of our conserved quantity within that cell.